So today we're going to continue to look at the Poisson distribution. Now that we've seen how to model appropriately, how to scale the parameter, the value of lambda, as necessary to fit the time or the volume or the capacity for a specific question, now we're going to look at combining different distributions. Before we get to the Poisson, just a quick reminder of discrete random variables and how we would have combined them together. So, let's say we had two fair three-sided spinners. So the spinner that we'll refer to as X has the outcomes 1, 2, and 3. Spinner we'll refer to as Y has the outcomes 2, 3, and 4. Since they're fair spinners, each of these outcomes are equally likely and 1/3. If we were to combine these, if we were to add these random variables, we would get a new sample space diagram for a variable we can call Z. So Z is what we get when we add the score from spinner X to the score from spinner Y. So we get this table, and I hope you recognize that each of these outcomes is equally likely, each of them having an outcome of 1/9. And we can produce the distribution, the probability distribution of Z by counting up the probability of getting 3 is 1/9, probability of getting 4 is 2/9, 5 is 3/9, etc. So we were able to produce a distribution when we were adding two random variables, but we did have to go through the process of producing the sample space diagram for the combination, and then from the sample space, making a new probability distribution. When it comes to adding Poisson distributions, we can actually combine the parameter as long as the time interval or the space interval or the capacity interval matches. So, by way of example, let's have a think about this. If we have 5 cars passing every hour on road A and 8 cars every hour on road B, for the combination of these two roads, yes, it's going to be 13 cars per hour. We have the two distributions. They represented the same time interval. We could have simply added them together. In general, if you have two Poisson distributions, each with their own lambda, as long as they represent the same time interval, you can simply add together the values of lambda when you're making a new distribution, which is distribution X plus distribution Y. Okay, so just a quick example for this. I hope it really hits home exactly what we're doing. If we had these two distributions, X has a lambda of 3.6 and Y has a lambda of 4.4. We've been asked to find the probability that adding X and Y equals 7. So we'll start with defining what that new distribution would be. So the distribution X plus Y is going to follow a Poisson of 8. From here, I could have called this new distribution Z or F or any value that you want, but it's not too hard to follow with X plus Y. From here, the probability of X plus Y equaling 7 is going to be, we can use the probability formula. We can use the probability function, e to the negative 8, 8 to the 7 over 7 factorial, or more likely you'll do this on your calculator. PCD 778. Both of them are going to get us the same answer, and the answer here is 0.1396. How about doing less than or equal to 5? So the probability that X plus Y is less than or equal to 5. This is hard to do with the formula. This is one you will definitely want to do on your calculator. PCD 0, 5, and 8 gets us 0.1912. So that's a straightforward one where we weren't actually even given the time interval. So we have to assume that they match. If there's more context, it is on us to check that that is indeed true. So here, we've been told that the number of cars passing an observation point in a 5-minute interval is modelled by a Poisson distribution with a mean of 2. The number of other vehicles passing the observation point in a 15-minute interval is modelled by a Poisson distribution with a mean of 3. Straight away, we should notice that these were two different time intervals, 5 minutes and 15 minutes. We're going to have to do some scaling somewhere. In part A, we're asked to find the probability that exactly 5 vehicles of any type, doesn't matter what type of vehicle, past the observation point in a 10-minute interval. Okay, so what I'm going to do first is to write down a distribution for the cars and a distribution for the other vehicles as they've been given to us. I'm going to scale them to match 10 minutes and then I'm going to combine them. Let's start with the cars. So we know that the cars follow a Poisson distribution of 2 and that is for a 5-minute interval. So C1 is going to follow a Poisson of 4 cars per 10-minute interval. Let's move on to the other vehicles. The other vehicles follow a Poisson of 3 per 15 minutes. We can scale that, 2/3, gives us 2 per 10 minutes. Okay, I'm going to make a new variable here, which is just going to be vehicles equals cars plus the other vehicles. Now that we have these two, C1 and O1, they're already in terms of 10 minutes, I know that V1 is going to equal 6. I know that V1 is going to equal 6 vehicles per 10-minute interval. Now that I have V1, that's what I'm going to use to answer part A, the probability of exactly 5 vehicles passing that observation point. So we're looking for the probability that V1 equals 5, and we can use either the probability function, since we're just looking for exactly 5, or we can use the calculator function. So e to the negative 6, 6 to the power of 5 over 5 factorial, or PCD 556. Both of them will give us an answer of 0.1606. Part B of the question asks us to find the probability that more than 8 vehicles of any type are going to pass the observation point in a 15-minute period. Okay, so it's a different time period to part A, so we are going to need to readjust and find what those new values for lambda are going to be. Since I know that V is already a combination of the vehicles, I can just focus on scaling V. So let's say that V2 is going to follow a Poisson of 9 vehicles per 15-minute interval. And now we're finding the probability that V2 is more than 8. Be careful here, we're going to rewrite this as greater than or equal to 9. And that can be written as a 1 minus less than or equal to 8. This is definitely one for the calculator, 1 minus PCD 089. Into your calculator, we get an answer of 0.5443. So we're still using everything we knew from modeling before, including the scaling, being careful that we're pulling out the right variable, but now we also may well need to combine different Poisson distributions together. So just be sensible in the way you're doing this. Use the subscript C1, C2, C3, etc. to keep track of which parameter matches which time interval. So I'll give you a chance to get some practice done. In the next lesson, we'll move on to looking at the properties of a Poisson distribution.